Good morning, everybody, or I guess it's afternoon, but that's not really the point. So today we're going to talk about section 2.5, limits at infinity, and you've probably noticed there at the bottom of the screen that this has 23 slides, and this is indeed kind of a longer, cumbersome section, but everything is really important, and you have a couple days to kind of mull it over, so don't get too scared, just take this video step by step, and if you need to, hit me with a pause, hit me with a rewind, any of that good stuff. So let's get started. So limits at infinity. And in contrast to infinite limits, what we studied in the last section, limits at infinity occur when the independent variable, typically x, becomes large in magnitude. Limits at infinity determine the end behavior of a function. So here we have a graph of f of x equals 1 over x squared, and we can see from our table that as we take x to approach infinity, our values go closer and closer to 0. So we plug in 10, let me highlight these. We plug in 10 and we get out 0.01. We plug in 100 and we get out 0.0001, and so on and so forth. So as x approaches infinity, our function approaches 0. And we can see that as we get closer and closer towards infinity, as x approaches infinity, our function approaches 0. And so a limit at infinity is just a equals infinity. And this is why it's not recommended that the first step you do is just plugging things in, because clearly if we plug in infinity, we're not going to get an answer that makes sense. But here we plug in 10, 100, 1000, and so on and so forth, and we get successively smaller and smaller digits. We look at the graph and we confirm, yep, as we approach infinity, our graph approaches 0. And another way you can imagine this is putting something that gets larger and larger and larger in the denominator. And 1 over something that gets bigger and bigger and bigger is going to get smaller and smaller and smaller. So as we do that, we approach infinity, or we approach 0. So that's the idea of a limit at infinity. Now with limits at infinity, we get horizontal asymptotes. And so if f of x becomes arbitrarily close to a finite number L, for all sufficiently large and positive x, then we write the following, and we say that the limit of f of x as x approaches infinity is L. And in this case, y equals L is a horizontal asymptote. We talked about vertical asymptotes last time, horizontal, horizon. This time we're talking about horizontal asymptotes. So what exactly does this look like? So here I've got a graph, f of x, and as I grow larger and larger and larger, as x approaches infinity, my graph, f of x, grows larger, and then at some point, it stops growing and looks like it wants to touch this line L, but it never does. And as we get negative and more negative and more negative, the same thing happens in the bottom. We're trying to approach this line M, but we just don't get there. So here we say that the limit as x goes to positive infinity of f of x, our function in black, of f of x equals L is this value right here, and L is a horizontal asymptote. The limit of f of x as x approaches negative infinity is M, and M is a horizontal asymptote. So how do we find these? So here I want you to do, let's see, evaluate the following limit. And this should just be pretty straightforward. We are going to get a horizontal asymptote in here, and I'll tell you why. So here our first step is we use our addition rule from our limit laws, and we separate the limit as x approaches a negative infinity of 2 and the limit as 10 times the limit of x, or the limit as x approaches negative infinity of 1 over x squared. So the limit of a constant is just going to be that constant plus 10 times the limit of 1 over x squared as x approaches infinity, negative infinity, is 0. So our limit approaches 2. And actually, when we do this again for the limit as x approaches positive infinity of our function f of x, we get 2 out as well. And why might that be? That's because we've got a horizontal asymptote there. So the graph of this bad boy looks something like this. As we get more and more positive towards infinity, our graph approaches this line 2, but it never touches 2. As we get closer and closer and closer, so we approach 2, but we never ever touch 2 because we can take numbers as large as we want and plug them in here. And while they approach 0, they never equal 0. We're always going to have some small leftover little bit that's going to be 2 plus that little bit. So 2 plus that little bit is not 2. We're going to approach that line. We're never going to reach it. And that's okay. Anything else? So furthermore, you can probably notice that we've also got a vertical asymptote at x equals 0. And why is this? And this is because we've got a divide by 0 error. If we were interested in the limit as x approaches 0 of f of x, when we go to try and plug in 0, we get a divide by 0 error here. And because there's nothing else with it, there's no plus or minus 1 or anything like that, when we plug in 0, we get an error. So we know our graph is going to shoot up in either direction, just like that. So hopefully I've beat this dead horse a little bit and you guys understand what's going on here. Now here's another one, and this one is a little bit tricky. So we know that the limit of 5 is a constant. That's just going to equal 5. But what about the limit of sine of x over root x? Well, we know from the squeeze theorem that this is 0. So what does this graph look like? Well, we know we're going to have a horizontal asymptote at 5 because we've got something left over. So I'll draw in my horizontal asymptote right here. But my function is sine. So it's sine divided by root x. And as x grows, my denominator is going to get larger, so my function better get smaller. So it's going to look something like this. And as we go towards infinity, we're always going to have 5 plus something. So we're never going to get to 5, but we are going to be able to get 5, or we are going to get close to 5. So our limit as x approaches infinity of our function f of x is equal to 5. But note that our function can never achieve the value of 5. Well, as it passes through, we achieve the value of 5. But so when sine of x is evaluated to be 0, that term goes away. But that's not the point. The point is that we can have horizontal asymptotes that look very different from one another. So here we've got one where our function crosses it multiple times, but the limit approaches it, but we never achieve that value in the end. And we've also got one where we approach it, but we never cross that line even once. So those are 2 different types of horizontal asymptotes that you may see. So let's talk about infinite limits at infinity. And this is going to be sort of your big boy grown-up pants concept. It's possible for a limit to both be an infinite limit, that is, the value equals infinity, and a limit at infinity, that is, x approaches infinity. And we call this an infinite limit at infinity. So if f of x becomes arbitrarily large as x becomes arbitrarily large, then we write the following, and we say that the limit of f of x as x approaches infinity equals infinity. And quick reminder, we know that if a limit equals infinity, it does not exist. So let's take a gander at what this might look like. Here I've got the graph of f of x equals x cubed. And it's pretty easy to see that as we increase x towards positive infinity, our function's going to shoot up towards positive infinity. And because this is a cubed function, as we decrease x towards negative infinity, our function is going to decrease towards negative infinity. So that's just a quick little intro for that one. Now, what can we say about functions when we've got x squared, x to the fourth, x to the sixth? Well, if we've got an even number in our power, we've got an even power, then both ends of our function are going to be pointing upward. That is, both of them are going to approach positive infinity. And as we go from x squared to x fourth to x6, we know that we go towards infinity faster and faster. So you would say that both the limit as x approaches infinity of x squared equals infinity, and you would say the limit as x approaches infinity of x to the power of 6 equals infinity, but you would say that this bad boy grows faster. And you'll see more about this in calculus 2, but I just wanted to introduce you to these concepts a little bit here early on. Now let's talk about odd powers. When we've got odd powers, we see that we are going to approach infinity as x approaches positive infinity. But as x approaches negative infinity, we're also going to approach negative infinity. And you can check these by plugging them into Wolfram Alpha, or if you've got a graphing calculator that you're not supposed to be using, you can plug them in there. But really super simple stuff. And again, we see that as we move from x cubed to x to the fifth to x to the seventh, we go faster and faster and faster towards either positive or negative infinity. So if we've got these patterns, then we better have a theorem that talks about the rules here. And indeed we do. This is going to be theorem 2.6 from your textbook. So if you want to see it written out just in a different font, go ahead and check that out. But let's let n be a positive integer and let p be a polynomial. And a quick reminder, a polynomial takes the following form. P of x is equal to an times x to the power of n plus an minus 1 times x to the power n minus 1 plus da 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 plus a1 times x to the 1 plus a0 times x to the 0. And here it's important that an doesn't equal 0. Everything else can equal 0 as far as coefficients go, but not an. So the limit of our function x to the power n when n is even as we approach positive or negative infinity equals infinity. And that's where we saw the graph of x squared, x to the fourth, and x to the sixth. Now the limit as x approaches positive infinity when n is odd, that is x cubed, x to the fifth, x to the seventh, we approach positive infinity. And as the limit approaches, as x approaches negative infinity, we approach negative infinity. So those are some hard and fast rules. Now what about 1 over x to the power n? Well, that's the same as x to the power of negative n. And as we do this, as we approach positive and negative infinity, we saw earlier that 1 over a very large number approaches 0, right? Because we think of 1/2 is bigger than 1/4, is bigger than 1/8, is bigger than 1/16. So as our denominator is increasing, right, these are getting closer and closer and closer to the value 0. And finally, if you're given a full polynomial, right, you're given something that looks like, let's pull one out of a hat, 3x to the fourth minus 6x squared plus x minus 10. If you're given something like that, it's a polynomial and not just x to the n. Well, it's going to be the same as if we just considered the leading term, so that an times x to the power n. And we'll see that in a couple examples. So here's our first example in that topic. I want you to determine the limit as x approaches positive and negative infinity for the following function. That is, p of x equals 3x to the fourth minus 6x squared plus x minus 10. So go ahead and pause your video and see if you can't figure this one out on your own. And if you can't, just keep watching. And if you get kind of close but don't make it, just keep watching. And if you nail it on the head, well then feel free to skip the video ahead 30 seconds. So we use the fact that the limit is determined by the behavior of the leading term. And this is that fourth bullet point in theorem 2.6 that we just presented. So our limit as x approaches positive infinity of our polynomial is actually just the same as the limit as x approaches infinity of 3x to the fourth. And we know that because x to the fourth, 4 is an even number, we're going to approach positive infinity. And again, x approaches negative infinity. Well, our polynomial, it might as well be just the leading term. And because 4 is an even number, we're going to approach positive infinity. So let's see another example. I want you to determine the limit as x approaches positive and negative infinity for the following function. And this time I've thrown a wrench in your plans. So go ahead and try this one out, pause your video, and try and see if you can't get this one and meet me back in the next slide. So we want to determine the limits as x approaches positive and negative infinity. I'm going to rewrite that in all my slides. And we just want to note really quick that the leading term is negative. So just like before, though we've got a polynomial, we really only care about this leading term. And so we've got a negative out in front, but we know that x cubed, let's see, I'm going to use pink. X cubed by itself in a limit goes to positive infinity. Well, a positive number times a negative number, so we have negative times positive infinity, that's where we get that negative infinity from. And we'll see the same thing. As we approach negative infinity, we know that we've got a negative times negative infinity. We know that x cubed likes to approach negative infinity. So we've got a negative times a negative. That leads to a positive. So that's the wrench that we threw in your plans. Let's continue. We're halfway done, but it gets a little bit more and more meaty as we keep going. So the behavior of polynomials as x approaches positive and negative infinity is an example of the end behavior of a function, right? Polynomials are functions too. Since we've already discussed polynomials, we will now talk about rational functions. I'm going to skip algebraic functions because it's just more notes that you don't really need to take. And we're going to talk about transcendental functions briefly. And remember, transcendental functions, that's e to the x, e to the negative x, and the natural log of x. So let's move right along. So we're going to start with some examples just to get you going. And remember that a rational function f of x is of the form p of x over q of x, where p of x and q of x are polynomials. So what do we do here? This one, I'm not going to ask you to pause because it's going to use a trick that I'll teach you in the very next slide. So keep on watching this video, don't pause. The first thing that we're going to do is to divide the numerator and the denominator by x squared. And why do we do that? We do that because when dealing with rational functions, it's easiest if the leading term in our denominator doesn't have an x in it. So we want to turn this into a constant. And if this was x cubed instead of x squared, we would be dividing everything by x cubed. So in this very first step, I think it's pretty clear to see that if we multiply by 1 over x squared divided by 1 over x squared, we're multiplying by the number 1. And that's really important, right? We're doing the same thing to the top as we're doing to the bottom, and we're multiplying the entire expression by 1. And by dividing the numerator and the denominator by x squared, we can break it up, and we're ending up with 3 over x plus 2 over x squared. And that leading coefficient in our denominator turns into a 1, minus 1 over x squared. So here, this 3 over x, that's going to go to 0. Our 2 over x squared, that's also going to go to 0. Our 1 over x squared, that's going to go to 0. And that's the power of dividing everything by x squared. We're left with 0 in the numerator divided by 1 in the denominator. 0 divided by 1 is 0. So we've taken something that looks really funky, something that we might not be able to plug a number into, and we've gotten out a value without having to use a calculator or some sort of graphing utility. So that's the end behavior of rational functions. So as we approach positive infinity, this function approaches 0. It approaches that horizontal asymptote of 0. Let's continue. We can see that, let's make sure we can see. So here's the graph of that function, just in case you don't believe me. But for 3x plus 2 over x squared plus 1, as x increases, the value decreases and approaches 1 or approaches 0. And as x gets more and more negative, our function approaches 0 again. And we can tell that we've got vertical asymptotes this time, official vertical asymptotes this time, because we have a possibility of getting a divide by 0 error in the denominator. And what does that mean? That means that for this portion, x squared minus 1, there are values that I can plug into this where I will get a divide by 0 error, namely positive 1 and negative 1. When I plug in positive 1, we get a divide by 0 error, and when I plug in negative 1, we get a divide by 0 error. So we know that as we approach positive and negative 1, our graphs should approach positive and negative infinity, respectively. So this is sort of wrapping it all together, the end behavior. Here's the next example. Again, it's a rational function, so it's a polynomial divided by another polynomial. And now that we've tested one out, I want you to go ahead and try and figure this one out. So to determine the end behavior of the function, f of x equals 2x squared plus 6x minus 2, all divided by x plus 1. So go ahead and pause and meet me in the next slide. So this one is actually a little funky. And I say it's funky because we get a slant asymptote this time, right? Very different from a vertical and a horizontal asymptote. But when you take the limit and you divide by x and you do the whole 9 yards, you figure out that as we approach positive infinity, our function approaches positive infinity. And as we approach negative infinity, our function approaches negative infinity. And why is this? Well, when we divide everything by x, we're left with 2x plus 6 minus 2 over x, all over 1 plus 1 over x. Now, the highest degree here is x, and the behavior of x is it's going to go towards positive infinity when x approaches infinity, and towards negative infinity as we approach negative infinity. And this is because 1 is an odd number. Anyway, a slant asymptote means that there exists this line that I want to highlight. Highlight it in pink. There exists this line that our function tries to approach while it's approaching infinity. And hopefully you can see that. But as it approaches, it's never going to go somewhere there. And this only happens when the degree of our numerator is 1 higher than the degree of our denominator. So the degree of our denominator is x, and the degree of our numerator is x squared. So you always get a slant asymptote when the degree of your numerator is 1 higher than the degree of your denominator. So speaking of all sorts of rules, here is theorem 2.7. And I'm not going to read this to you because I think that that would be really patronizing, because you guys can pause this video and read it yourself. But if the degree of your numerator is less than the degree of your denominator, then da 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 da. So we've got the definition of a rational function here. We've got all that good stuff. So go ahead and press pause, read this, copy it down into your notes. We've already seen all of these things in action. And finally, the end behavior of e to the x, e to the negative x, and the natural log of x. Again, just pause your video and write these down. These are going to be things that you just have to memorize. You can't really cheat around them or anything like that. You just have to memorize them. But if you know how to draw these functions, then you're going to know how they behave. And that's important. So after you're done pausing this video, that's all I've got for you this week. Expect a written homework pretty soon. I wanted to get through all the stuff that we could as far as limits go. That way written homework 1 is all limits all the time. They are going to be more challenging problems. They are going to take you a while, but I'm going to give you a long time to work on them before submitting them. So that's it for me. I will see you in the next video.